Now let's look at this plot again. What are we looking at this equation? Delta G is for free energy change, of course, from initial state, which is pure liquid, to final state, which is liquid plus a solid nucleus with radius of r is two terms together, right? The second term is a red one representing the interfacial energy contribution. Its second term is always positive. The first term is always negative. It's a function of r to the power of 3. It's a volume free energy term. So this is our total free energy change during this so-called initial stage of nucleation. In order to find the so-called critical nuclear size, which is the maximum, mathematically, how do you find the maximum? Well, the red, the blue, they add up together to be this black one. And to find so-called local maximum, we just need the first derivative of d what? D delta G, the whole thing with respect to the radius to be 0. And how do we do it? Very simple, right? So we are going to do the first derivative with respect to the radius, which is the 3, and this 3 would cancel. Minus 4 pi r to the power of 3 now become r to the power of 2 delta GV we keep. Make sense? And then plus 4 pi we keep, but now r square become 2r, and 2 times 4 become 8 pi, right? R, the gamma term we keep. And from here, we rewrite, okay, the 4 pi and 4 pi we would, actually 4 pi r would cancel. We would have 2 times gamma SL equals r, that's the remaining r, times what? Delta GV. As a result, actually, this r should be our r star, the so-called critical radius, so-called r star, would be 2 times of interfacial energy divided by your driving force, or the volume free energy change, which depends on the so-called undercooling. Okay, this is a very important relationship. It tells us, okay, the so-called critical radius, the radius where you would reach this top of the hill, is given by this one. Okay, and we would say if you form a cluster within the liquid, but it has radius smaller than this R star. If it's here, naturally, where would that cluster go? Become larger or smaller? Well, if I'm here, naturally, in order for it to grow, the energy has to increase further, which is not spontaneous. But on the other hand, it's actually natural for that small cluster to roll back down, to decrease in cluster size, to shrink. Make sense? That's what it means. On the other hand, if occasionally I have a cluster that is slightly larger than this R star value, then what would happen? Well, it's actually, in order for it to shrink, it actually has to increase energy. But it's much more easier, spontaneous for that cluster to continue to grow, roll down the hill. Okay, so that's kind of the implication or meaning for this so-called R star value, the critical radius. Okay, and if we recall, what is delta GV? The so-called free energy, volume free energy change from liquid to solid is a function of delta T, undercooling, proportional to delta T. Then if we plug this relationship back into the R star, what would we get? We're going to get something like this. R star would be still 2 times of gamma divided by this delta GV term. What is delta GV? LV delta T divided by Tm. As a result, what would happen in terms of our star? We would have the critical nucleus radius size would be 2 gamma. LV, we keep it in the denominator. Tm, we have to put it in the numerator, and then delta T, we keep it here. What does this mean? This means the so-called critical nucleus size or radius or star is linearly proportional or inversely proportional to delta T or proportional to inverse of delta T. What does this mean? When delta T become larger and larger, which means we are lower and lower, we are colder and colder, our star become smaller and smaller and smaller, right? When delta T, remember, is how much we are below the melting temperature. When delta T become larger, which means we are hotter or colder. When delta T become larger means we are colder, our star become smaller and smaller. On the other hand, when delta T becomes smaller and smaller, gets towards 0, which means we are getting closer to what? When delta T goes towards 0, which means we are getting closer to melting temperature Tm, our star would become, when delta T goes towards 0, our star become infinity. Okay. So what this kind of implication is, as delta T, the so-called undercooling goes towards 0, our star, the critical size, goes towards infinity. Critical size goes toward infinity. That's another way to say the so-called homogeneous nucleation. This nucleation, this solidification by homogeneous nucleation form uniform solid cluster will not occur for small undercooling. Small undercooling is that T is small. But our star is infinity, which means what? Any size cluster I form would be smaller than our star. If it's smaller than our star, it's natural for that cluster to what? To grow or to shrink? To shrink back. So that's why we say homogeneous. This nucleation solidification by so-called homogeneous happens everywhere, not at a specific location, will not occur when delta T goes towards 0, when your undercooling is very, very small. Okay?